Hey everybody, Dr. Retzek here. This is our third video in section 6C, where we're learning about orthogonal complements. Let's get started. So this is section 6C, continued. And the setting is what it has been. So you have this big box full of stuff. This is an inner product space. You can call it capital V. That means it's a vector space. And as usual, this is equipped with an inner product. Nothing specific, just meets the definition of inner product. Now, for the purposes of this discussion, we will be thinking of a subspace sitting inside V. Maybe let's call it U. Use a subspace and we can form its orthogonal complement. Let's say U perp in green. And again, we draw these just brushing up against one another because we know the only vector orthogonal to itself is 0. So the only thing that U and U perp can share is the 0 vector, which is this vector right here. So there's 0 where they touch, otherwise they're disjoint. Okay, so we know already from our discussion in 6C that we can express capital V as U direct sum U perp. In other words, each object in the box V can be written uniquely as something from the red plus something from the green. When you believe that each object in V can be written uniquely in that way, it leads to an idea called orthogonal projection, where in essence, the orthogonal projection of a vector in the box V is gotten by expressing that vector as something from the red plus something from the green, and then just ignoring the part from the green. That's how orthogonal projection works. Precisely, we're going to define this map. So that's a capital P. It's subscripted by a capital U, which refers to the subspace in the drawing. The map takes inputs from V and produces outputs in V. That map is called the orthogonal projection onto the subspace U and is given by, well, we said it a moment ago. You feed this projection some vector V. It's going to express V as something from the red plus something from the green, and then just ignore the green part. In symbols, that looks like this. The orthogonal projection, PU, acting on little v, comes out to little u, where little v is little u plus little w in the direct sum of u and u perp. In the picture, this is thing from the red. This is thing from the green. So when you feed V into the projection, it just keeps the part in the red. So in that definition, the role players are here. You got some random vector V, might be in neither green nor red. You know for sure you can write it as something from red plus something from green. You know there's only one way to do it because that sum is a direct sum. And when you feed that vector, u plus w, into the projection, it just lops off the w part and keeps the u. And that's how orthogonal projection works. If you want to see a mapping diagram rather than a single picture, maybe we could draw something like this. So visually, what we have is something like this. Here's V. Here's U sitting inside it. Here's U perp sitting inside it. Here's a typical object in V. The projection takes objects in that box and produces outputs also in that box. So I'll try to replicate the subspaces. There's U again. Here's U perp again. And what happens is, if you take that input vector on the left and express it as something from red plus something from green, so that V equals U plus W, then where that gets sent by this map, that individual object on the left gets sent just to U. So you look at this picture and you realize, oh, wait. So this thing is like way not one-to-one. Because all sorts of different objects over there all go to the same red part. Any two things that have the same red part have the same output because the green part just gets lopped off. So if you had U plus W1 and U plus W2, they would both just get sent to U. So this thing's way not one-to-one. You can ask all sorts of questions about this, like is it really linear? What's the range? What's the null space? All sorts of questions. These are things that we will address in video 4 on Monday. At this moment, I thought we could look at a concrete example and try to connect it back to our natural sense of perpendicularity. In this example, let's bring it back to our roots, the good old days. Vectors, Calc 3. So here's R2. Now imagine you got two subspaces sitting in here orthogonal to one another. Subspace number 1 in red is right there, the so-called x-axis. Call that U. U perp, okay, well that's all the things perpendicular to the red. This is only a two-dimensional space. U is one-dimensional, so U perp is the other dimension. So let's say in green like this, so-called y-axis. So there's U perp. Okay, now let's take a random vector, just an arbitrary vector in R2, like say that. So that's playing the role of V. Now let's think about what the projection onto U does. All right, well, certainly we get answers in the same vector space. This is going to map R2 to R2. So you can see those subspaces still hidden in there on the output side of things. So there's U again. And here's U perp again. And now imagine how this works in this concrete example. So what did we say we were going to do? Okay, you take the arbitrary vector V and you try to write it as something in red plus something in green. So if we try to take this V on the left and write it as something in red plus something in green, then those would be the two somethings. Those are the unique vectors, one red and one green, whose sum, like by, what would we call it back in the day, like tail to tip method or something? Those are the two, one red and one green, that add up to V. So in our drawing, maybe we would call this one little w, and we would call this one little u. And so all that happens when you do the projection is your answer is you keep the red part and just lop off the green part. So this vector here is the projection. You can see it lies in U, and it's just the original red part of the original vector V. If you want to see it sort of really, really geometrically, just check out. Imagine you were just going to compress the vector V onto its shadow down there in the red axis. That shadow, that is the output. And that's why they call it a projection. It's as if you shine a flashlight on V directly perpendicular to the red space and just take the shadow as the output. You'll recognize this as one of our very first ideas all the way back at the start of chapter 6. It was the key ingredient that went into Cauchy-Schwarz, I think, which has been huge for us. Do you remember the idea of the orthogonal decomposition? In that discussion, we were able to take a vector and write it as a piece that's a scalar multiple of some other vector plus a piece that's perpendicular to that other vector. And so this is just generalizing that idea. Now it's not a single vector, you're projecting into an entire subspace. Though in this example, that subspace is one-dimensional. And this vector is the good old projection. This one right here is projection onto the x-axis. So that's it for the idea of orthogonal projection. You have a subspace, you write a vector as something from that subspace plus something from its perp, and then just ignore the part from the perp. And that's how you do the orthogonal projection. Your reading from this point onward is to read the big theorem. I think it's got like 10 parts or something, which is like all the facts you'd ever want to know about orthogonal projection. And they all make really good sense in terms of these images and in terms of the definition. And that will be the 4th video on section 6C. All right, keep reading, keep up. Let me know if you have any questions or comments, and I'll see you next time. Bye.